So in working on writing a solution in a language, we have to be able to describe the problem. And most problems you can break out two basic parts of the problem: the data and the steps you need that usually work on that data to produce the result. So we're going to see for example, when we get into object-oriented programming, we're going to marry those two together so the data will have certain steps related to that data. But in any problem, we're going to break it down in basically those two domains: the data and the steps needed to produce the result. So computer languages provide notation to represent the data. So in C++ and Java, you could say int some variable name, and it would allocate some memory and allow you to store some bits in that memory, and the data type told it how to interpret what that was. So if it was int, it knew that bits were organized a certain way. So when you said add two of these, it applied an interface, which is the interface of how to add, to actually do that. And the other part of a language is actually controlling the steps involved, which are your control structure constructs. So let's look at those. So in control structure, we have sequential, selection, and iteration. And then we have procedural abstraction, which is defining functions. So you covered that on your first class, and I hope your first class emphasized that when you write programming, you want to avoid duplicating, avoid doing the same code in two different places or three different places in your program. So let's look at the data. All the data in the computer are a sequence of bits. The data types are how we associate meaning to these bits. So the actual bits, if you say this part of memory is an int, it will have a certain meaning of the bits to how you represent it as an int, which will be different than if you say these bits here are a floating point value. You can't just interpret the bits as a floating point and then also look at it as an int, because they have different ways that they use the bits. So that's why every piece of data in the computer you have to know what type of data it is in order to associate meaning to it. And data types also have related things you do that data. So if you have an int, you do add, subtract, multiply, divide. If you have a string, you do concatenate, you do substrings of it, so you have certain things you do. If you have arrays, you have certain operations you do on arrays. How many things are in the array, get an element out of the array. So for every data type, you have very specific interface to how you access or work with that data. So data types are also related to common ways we represent data in the problem. So we may have a problem that has fractions or a bank balance. So when we start talking about a certain problem we're solving, you can think of what operations do you need to do on that data, and so that defines a data type. And in fact, part of what we're going to learn in object-oriented programming is defining our own data types. And in algorithms and data types, the data types will be the interface that we're going to put our algorithms inside of. And that's going to be what's called an abstract data type. So when we create a new type of data, we're going to use what's called procedural abstraction for the data, but we're going to do it actually in an object-oriented way. So we're going to actually be doing abstraction through encapsulation in an object. We'll learn more about that. So we create abstraction for new data types, and we're going to call these, for a particular data type, that's going to be an abstract data type. So we're going to do, for example, a type of data later called a list. And so we'll have an abstract data type interface which lists the methods that a user would expect a list to have. And so you can look at it this way: here's the user or some client code that's going to use that data type. So they would define some place of memory they want to store that data, and once they've stored that data, they have a variable that points to it, and then they can call methods on that data to do things. How it actually does the things and how it actually represents the data in bits in memory is inside the definition of your abstract data type, and the user doesn't need to know that. They just need to know the interface. What methods do I call to work with this data? So the user or client of an ADT has a very specific interface that they can rely on certain predefined operations to work. So if you consider the integer type, you expect it to have operations like add, subtract, multiply, and divide. And as long as the integer type of data implements the standard operations, you don't care how the operation's carried out under the hood, or what form of bits in the computer represent the integer. So this provides an implementation independent view of the data. And that's the whole reason we have an abstract data type, is we have an implementation. We don't care about that. The interface works, and so the data type becomes implementation independent. How it's implemented is independent of the interface. Now let's do a date example. So an abstract data type for a date may have the following interface methods. It may have a method to get the number of days to another date. Well, spelling's a little off there. It may have a method to get the week number of the year. So if I have a certain data that's a date, and I can say, well, get the number of what week is it in the year. So it might be week 22 of that year. We might have a method that advances the date by a number of days, so it changes the date. Or we might have a date that it changes the date to a certain month, day, and year. So the data actually gets replaced internally, however it's being represented to this new value. And we might return the date. So we might ask that data type to return the date in a certain format and have a way of specifying which format we want. So maybe it returns a string that's formatted in different ways. So how you represent the data internally doesn't matter. So that is independent of the implementation. I mean, the implementation, how we do it internally, is independent of the interface. So now we're going to do a little bit about how we study algorithms. And at the bottom here, you've also, I hope, looked at the first 11 slides of the Princeton slideshow. And he shows you a little different take on this. There's some overlap. But one of the advantages is seeing how to solve different problems with various approaches will teach us how to recognize patterns in our problem solving. So as we learn how a lot of these problems through this class are solved, we're going to learn patterns that we can apply to our own problems when we see similar problems. Different algorithms to solve the same problem will use different computer resources. So you're also going to learn an appreciation of when you design an algorithm, how to think about how efficient it is, how do you make it more efficient, and how do you measure that. This mentions here that some problems may be too big to solve, so you may want to either find another way of solving it, or as you go on in computer science, you'll learn more about figuring out if it really is unsolvable. And we may have to decide on different approaches because of trade-offs. So we're going to start Python the next series of slides.